final speaker for this session, actually, we go back to UQ. Gabriele Tartaglino-Mazzucchelli, and on TTbar and high-spin deformations of integrable field flares. Thanks, Gabriele, when you're ready.
Yeah, first of all, let me thank the organizer for this invitation. It was quite a surprise, and I'm very pleased to have the opportunity to talk in this audience about some recent results that I've obtained with a lot of great young people that helped me, some of my PhD students, and especially some of these young postdocs. And well, Christian is about to apply for a permanent position, so they've all done some great works, and I'm really pleased to tell you some of our results here. So the aim of the talk is to give a short overview of how to construct new infinite families of two-dimensional integrable field theories based on what are called TTbar deformation and their extension. And what the tools that I will try to use will be essentially deformation driven by some operators that are composite in conserved currents. And we will engineer this deformation by using appropriate couplings with some auxiliary fields. And the way that we arrive to this is really finding some nice analogies between results in 4D-dimensional self-dual electrodynamics and integrable system in 2D. So let me tell you what actually is TTbar and what are the high-spin generalization that I'm interested in this talk. Well, if you have never seen TTbar, well, you've probably seen these slides several times here in Australia in my talks, but the whole story started with this beautiful paper of Zamologico from 2004. Essentially, what Zamologico realized is that you can take any arbitrary two-dimensional quantum field theory. You just assume essentially that there is translation invariance, and then you always have the existence of a local energy momentum operator, which is a conserved current. And within the theory, you can prove that there's always exists a local operator, which is given by the determinant of T mu. Now, for a CFT, this operator just becomes the product of the holomorphic and anti-holomorphic energy momentum tensors. And this is why the name TTbar appeared in the literature. What is remarkable about this is that the operator is irrelevant. And despite that, thanks to conservation equations and various other properties of this particular combination of the energy momentum tensor, can be proved to be quantum well-defined. And this is quite remarkable because it goes somehow against the law of renormalization in QFTs. So essentially, you have this operator in the spectrum, and then you can start to try to do wild things. Instead of doing some marginal deformation, you can start to think, okay, why don't I take an undeformed model? Here I will generically think about a Lagrangian L naught, and I want to start to deform it. I want to start to take the parameter lambda and use this local TTbar operator and get into a new model. And you can iteratively do that and get to some type of differential equation that will be a key object that I will study in this talk. And this is an example of so-called TTbar flows. So essentially, you can take a seed theory and try to solve some differential equation that will provide a line of a deformed model. Now, despite this very interesting observation on Zamologico, not much happened until 2016, when actually two beautiful papers appeared almost at the same time. So Smiron, Zamologikov, and Cavaglianegro and Tateo noticed some really remarkable properties of these deformations. And in particular, very relevantly for this conference, is that if you start from an integrable seed theory, so a two-dimensional quantum field theory that is also integrable, and you perform this type of TTbar deformation, what it turns out is that you generate a line of integrable QFTs. So integrability is really preserved by this type of deformation. And then it was also shown in these papers that somehow not only you can have integrability, but even for an arbitrary quantum field theories, you can somehow solve this type of deformation. So there are many observables that can be computed exactly if you know such observable in the deformed case. And the simplest and most famous example is the spectrum over a cylinder of particular QFTs. In fact, if you know the energy and the momenta of some states of a QFT over the cylinder, you can compute exactly the same data over the entire families of flows. And if you start from a CFTs and you have this line of deformation that passes through a CFT, you can actually write a very explicit formula where you have this radius of the cylinder and then some square root and the data of the deform model. Okay, and this is somehow the first example of the solvability of this TTbar deform QFT. Now, in 2016, in the same paper, Smirno and Zamologikov actually noticed that you can even do other type of deformation that are similar to TTbar. And in the case of an integrable QFT, assuming that you have some set of local higher spin currents with spin S, which I will denote here with capital J, there exists always an operator, a composite operator, which take this particular form. You can define it as the coincident point limit of the products of the currents in this combination. And again, similar to TTbar, it's very non-trivial and remarkable that this operator always exists in any integrable quantum field theory. And if you take actually S equal to 2 in this combination, you obtain a precisely TTbar operator. So not only you can start to study deformation by this determinant of T mu, but you can also start to study deformation of integrable field theory by very complicated composite operators constructed out of local spin currents. And so in principle, you can try to solve, for example, Lagrangian flows written in this form with these composite operators that will be driving the deformation. So this is way more complicated than TTbar. It has been studied in some beautiful paper by Zamologikov, and Tatea in the last few years. And recently, we tried to actually understand a bit better this deformation, at least at the classical level. Now, I mean, you might be aware, but these TTbar deformations have become somehow a field by themselves. In fact, since 2016, the deformation has been proven to have a lot of very interesting properties. Many observable, not only the energy spectrum can be solved in terms of the undeformed models. For example, the torus partition function can be computed exactly through this deformation, and remarkably preserve model invariance if you're deforming a two-dimensional conformal field theory. And the S matrix is also computed exactly. Turns out to be a simple CDD factor, which justifies the fact that integrability is preserved in these deformations. And also correlation functions and algebraic properties have been studied in the last few years. And of course, one of the topics has been also studying, trying to obtain exact classical Lagrangian flows, which is what I will be mostly focusing on in the talk later on. One of the beautiful aspects that was realized and proved in several contexts is that essentially these deformations preserve a lot of the nice properties of the starting theory, including symmetries and other properties that you might have in the undeformed model. And for example, if you start from a conformal field theory, it's even remarkable that somehow, even though the deformation breaks conformal invariance being irrelevant, it turns out that actually the Virasoro algebra is somehow non-locally still defined. So there is still a Virasoro that arises from the CFT, but it has a non-local realization, which is very complicated. And there's some nice work by Guica and others. And what we did a few years ago is actually to show that even supersymmetry is preserved. So you start from a seed theory, which is supersymmetric. You do this TTbar deformation, and supersymmetry is also preserved, as well as many other symmetries that have been noticed in these models. Now, I don't have time to give you an overview of all that has been done in the last 9 years. But the punchline is that this TTbar deformation gives really a new windows to try to understand local quantum field theory, and has found a really surprising connection with the theories of quantum gravity, and I found a wealth of application. And I suggested to look at this a very nice review, including the beautiful PhD thesis of my collaborator, Christian Ferko. Now, I want to switch and start to look at something concrete. And essentially, I want to focus on constructing Lagrangian flows and underline some of the dynamical features that are preserved by the deformations. So the first example of Lagrangian flow that was studied in the original paper by Tatea is very simple. Essentially, what you want to try to do is find solution for this set of differential equation, which looks really simple in this form, but actually it can be quite a nasty PDE because the energy momentum tensor will depend on the position in this flow, and it's quite complicated to actually compute it point by point. So it's not trivial to solve this equation. So it's a nice problem to even just try to do that. And essentially, in the first paper, Tateo and his young collaborators did the simplest thing that could be possible to do. They consider a boundary condition in this problem that was given by a set of free scalar field Lagrangian. So you start with a knot where you have n free bosons, and you are able actually to solve explicitly this differential equation, and you obtain the following Lagrangian. Remarkably and fairly unexpectedly, the result is essentially string theory. In fact, what you get is the Nambu-Goto string action in a static gauge. And this is probably the simplest example of realization of TTbar and its connection to strings and gravity. And it's also known that the resulting Lagrangian is an integrable QFT. You might now want to try to do the same with this mirror homological deformation with ISP operators. And it turns out to be way more complicated. Essentially, the only papers before last year where explicit Lagrangian flows were given is this paper by Rosenhaud and Smolking from 2020, where they tried to do the same that Tateo did for the TTbar in the case of the free bosons, but they did it only for one single free boson, and they try essentially to do the same type of deformation with an IOSpin operator. Now, I'm not going to look explicitly at the results. Essentially, you need to do an appropriate ansatz, both for the Lagrangians and how actually all the IOSpin currents are going to be deformed through this flow. And you can write down a system of coupled ODEs, which unfortunately doesn't have, at least yet, we didn't, neither these authors, neither us, managed to solve it explicitly, but you can find a series solution in lambda that arbitrary order if you wish. So essentially, you can prove that you can indeed construct this mirror homological Lagrangian, and here I just list some of the first order of the solution. And it's clear that these deformations are way more complicated than TTbar. You need some better techniques, and this is what we tried to actually do recently, where we introduced some auxiliary field to study this type of deformation better. And in fact, this paper didn't actually prove that integrability is preserved by this deformation, but it's easy to do it with other techniques, as I will see later. I want to also comment about a four-dimensional case. In fact, what was quite natural to do after seeing all this research for a few years was to ask the question, what happens if I try to actually study similar deformation but in higher dimension? And what Negro, Conti, and Tateo did in 2010 was a very nice and natural problem. They tried to reverse engineer a possible TTbar flow. So they knew that Nambu-Goto was emerging when you were doing the deformation into dimension, and they started to ask the question, okay, maybe I can find some very simple and nice Lagrangian that plays an important role in string theory. Will this Lagrangian have also some TTbar flow? And this is precisely what they did. They considered the Maxwell-Bornfeld model, which is this Lagrangian shear that has some square root similar to the Nambu-Goto case, which can be considered as a higher derivative generalization of Maxwell. So the first term here is the well-known Maxwell Lagrangian, and then you have an infinite tail of correction that are associated to alpha square parameters. And then what they did, they just did an exercise. They took derivative with respect to this parameter. They computed the energy momentum tensor, and they asked, is this going to be a TTbar-like flow? And they found that indeed it was the case. And the operator that drives this deformation for Bornfeld is very similar to the two-dimensional case. It's a quadratic operator is the energy momentum tensor given by this expression. And the boundary condition in solving this equation is just that lambda equal to 0, you have Maxwell theory. And this was a first example of theories of electrodynamics that did prove to have some TTbar flow interpretation. After this paper, there appear many other papers where, including myself, my students, we try to understand whether other type of electromagnetic models were satisfying similar flows. And we systematically found that this was the case. And in fact, then we realized that it turns out that every duality invariant models of electrodynamics needs and has to satisfy some type of TTbar flow. And more specifically, what we consider is that you can somehow extend nonlinear electrodynamics by considering some Lagrangian that is dependent on two variables, essentially a variable S and a variable P, that describe all the possible independent Lorentz invariance combination that you can take out of the Maxwell field strength. And it is well known that, and it's important actually in the study of string theory and electrodynamics in general, that you want somehow to modify the well-known electromagnetic dualities of the equations of motion of Maxwell, which is in the free case the symmetry that you have in switching F with the Hodge dual in the equations of motion for Maxwell theory. This can be generalized to the interacting nonlinear case of models of electromagnetism, and it has a long history. And it was realized that actually you can impose nonlinear self-duality conditions by setting some specific PD satisfied by this Lagrangian. So this goes back to work of Gaillard-Zumillon, then it was revisited by Kozenko and Tyson and many others. So, but nicely enough, if you impose this PDE on this type of Lagrangian, you actually obtain some models that have some duality for the equations of motions. And this is a fairly non-trivial PDE, but what and constructing solution is in general not this simple. There are techniques I will comment about that are actually related to auxiliary field, but another way that you can, we did realize that you can impose this condition is by proving this theorem. So essentially you can prove that any nonlinear duality invariance theory in 4 dimensions is satisfying this equation if and only if there exists a TTbar-like flow. So assuming that there is a continuous differentiable line of models. Okay, so somehow this is a quite remarkable result for 2 reasons. One, you can use this approach to actually construct new models of self-dual electromagnetic duality invariant electrodynamics. But on the other hand, you can also realize somehow that there is a nice new interpretation of this flow. Now, some comments for later. Essentially, I was saying that it's not easy to find the solution for this equation. Well, there are techniques based on auxiliary field that you can use to actually construct duality invariance models. Then you turn the partial differential equation in a difficult algebraic problem where you need to integrate auxiliary field to obtain actually duality invariant models, but in principle you can do that. And this is something that Ivanov and Zupnik did in 2002. And what is we realized it is quite remarkable is that ideas developed for these 4-dimensional models can actually be used to construct new infinite families of 2-dimensional integrable field theories. And I want to show you how and exactly what. Now, the playground for this 2-dimensional integrable field theory is essentially the formation of the principal current model. So the principal current model is a prototypical example of a 2-dimensional integrable field theory, and it's a starting point for several deformation and construction, including Benjamin-Witten model and etc. And the degrees of freedom are essentially maps between 2-dimensional space-time and the Lie generic Lie group G within Lie algebra little g. And the variables in these models are described by through Murray-Cartan form that are defined this way. And the Lagrangian is just a simple trace of G plus G minus, where I'm using here light coordinates. Now, it turns out that you can do something similar to nonlinear electrodynamics. You can come up with a set of variables that seems similar, look similar, and for good reason are similar to the SMP introduced here. So you introduce this combination of traces of G plus and G minus, and then this P squared that is a bit more complicated. And you can ask yourself, if I actually make an extension of this PCM by considering some generic Lagrangian as a function of these 2 variables, can I find the integrability in these models? And remarkably, the answer is yes. And the equation that enforces integrability of the model is precisely the sum of 4-dimensional duality invariant theories of electrodynamics. And this was somehow shown, and I have to say that this is strongly a contribution of Christian Ferko. This was shown in these two papers. And what is nice about this is, well, first of all, you realize that there are infinitely many new integrable models based on essentially the information of the PCM. But also because there is this connection with electrodynamics, it's natural to ask questions like, can I use actually techniques that were used in electrodynamics to solve this equation and construct new integrable field theories? So can I use auxiliary field formulation? Can I prove, similarly to the theorem that I showed before, that all these integrable deformation are in one-to-one correspondence with the TTbar-like flow? Can I also extend this to construct Smearon's homological deformation, etc.? And what we had found in the last couple of years is that all this is possible. So, and essentially the trick is to really use these auxiliary fields. And we introduce a two-dimensional version of that. So besides the variables of the PCM, we introduce some auxiliary field V plus minus that are a vector and X value in the algebra of the group G. And we just consider this simple action. So here you essentially have the PCM Lagrangian with an opposite side. Then you have some terms that depends only on the auxiliary field, and then you have a coupling between the auxiliary and the V field. And then you write some interaction function. You have some function E that is in principle completely generic that will encode all the nonlinearity of these models. And the key point is that you set this E equal to 0, integrate out the auxiliary field, and you turn back to the PCM. So, but then when you turn on this function E, the integration of the auxiliary field is incredibly complicated. It's not a simple task. But this will naturally lead to an infinite new families of higher derivative Lagrangian that are based on the variables of the PCM. And we refer to this deformation as auxiliary field sigma model. Now, the key point is that you look at this and you try to understand what is the condition that I need to impose on this interaction function E to have integrability, and you can prove a very beautiful theorem. So essentially, you can show that if you choose the interaction function to be a function only of specific chiral traces of the S auxiliary fields, so a generic function of trace of V plus to the K and trace to the minus to the K with some integer, arbitrary integer K and L, what you find is that all this infinite family of models is in fact classically integrable. And this was shown in a set of, in a series of paper. The first case was just considering the case of K and L equal to 2, which is linked to TTbar-like deformation. But then nicely, you can extend this to actually obtain higher spin deformations of these models once you consider more arbitrary traces in here and the power of this auxiliary field. Now, it's actually very simple to prove integrability. It's quite remarkable. Remember that there is an infinite family that is described by this function E. And despite how many possible integrable models that you can create, the Lax connection takes a very simple universal form. So essentially, it's a deformation of the Lax for the PCM, where you have a new term that depends on a frag J object, which is a linear combination of the Maria-Cartan term and the auxiliary field. So this looks completely universal for all these models, but the key point is that depending on the different function E, once you integrate out the auxiliary field, this will become a very complicated and different functions of J. But in any case, you can just do this answer for the Lax, and you can prove that the equations of motions are equivalent to the conservation of this frag J current. And this turns out to be equivalent to the flatness of this Lax for all these models. And I want to show that actually this is somehow related to TTbar and the Smearon's homological deformation. And you can easily see that, for example, if you consider the interaction function given by this combination, where I take a parameter lambda and there's a trace of some integer s v plus and trace of v minus to some power s, which I call a nu s for some s bigger or equal to 2. Now you can work to leading order in the parameter lambda, eliminate the auxiliary field V, and see what the action is going to be. And what you find is that essentially you find the first order deformation by the Smirnov homological operator. So this is somehow a generating, similar to a generative function of an infinite number of models that depends on this particular action. Okay, so if you take s equal to 2, it's just a deformation by a TTbar operator, but you can do also higher spin deformations, where in fact it's well known that these combinations are conserved currents of the PCM. So marginal interaction function implement deformation by the trivial function of the conserved currents. And as I was saying, for instance, the class of interaction function E, whether you take s equal to 2, can be proven to be one-to-one correspondent with all TTbar-like deformation. Okay. Now we wrote 7 papers in the last couple of years where we actually extended this to many other cases. You can prove not only that the lux is flat, but you can also obtain the monodromy matrix. You can prove actually that Poisson bracket takes the Maliev form, which implies that there is an infinite number of charge in evolution that can be constructed for the monodromy matrix in the case of the PCM. But then not only you can construct this data, you can also start to obtain local high spin currents out of this procedure, which at least to our fairly ignorant knowledge, we didn't know actually how to do it in general. We didn't know whether there was a prescription to construct these high spin currents in general. And then with fairly small modification, you can not only deform the PCM, but we can deform the PCM with the Wetzmino term. You can take a Young-Baxter deformation of these sigma models and deform it with this auxiliary field. You can semi-symmetric space-time sigma models and also take this deformation, and you will always have these infinite families of deformation. And all these are actually quite interesting because they are examples that are studying in holography for ideas CFTs, and they're all proved to be integrable. And this approach can also be used to actually understand T-duality in the context of non-abelian T-duality in the context of TTbar. It can also be used to study somehow the geometry of deformed solid surfaces. And it can be used to prove that actually instant-like solution in this type of models are preserved under stress TensorFlow, which is somehow a generalization of some results that we obtained with Theo for instantaneous in 4 dimensions. Okay, let me turn to conclude the talk. So essentially what is happening is that the community, or at least actually various communities, not only FTH, but also integrability and other communities are actually trying to understand and find several applications for this TTbar-like deformation. And in fact, this applies to integrability, understanding in new ways RG flows, and it even impacts the study of quantum gravity and holography. And we are still exploring new tools to learn more about this TTbar and Smirnov homological deformation. And I think that these auxiliary field techniques have provided some, well, first of all, they provided new infinite families on integrable deformation, where on one hand, in 4 dimension, you can impose duality invariance in a manifest way. And in 2 dimension, you can have integrability in a remarkably simple way. Now, what you can do with this auxiliary field, well, you can try to understand better the algebra currents and the symmetries in models. There's some work in progress we're doing in which we can show actually the structure of the Youngians, so it's modified in these models. You can try, actually, one of the open questions is to try to understand how this auxiliary field deformation can be used to engineer integrable deformation that passes through non-conformal point, because all these PCM-like theories, they are conformal. Even though the deformation are not conformal, we would like to understand whether we can study this TTbar-like deformation, for example, of Sam Gordon or other integrable models that have potentials. And so far, we don't know how to do it. We can find application to ideas CFT, including SPN1. And it would be nice to understand actually if this connection between duality invariance in 4 dimension and in other actual dimension and integrable models can be engineered also by using, for example, Chen-Simon or abelian models in dimension higher than 2, or by using self-dual Young-Mills theories. And there's actually a paper of that does this in the 4-dimensional case. And it will be, of course, nice to understand better quantum properties. In the case of TTbar, partition function, correlator, and etc. have been studied, and we would like to understand whether by using auxiliary field we can do the same also for Smirnov, some logical, and etc. And with this, I conclude, and I really thank you for this opportunity.
you. So where are we? Do we have any questions?
Yes.
Vladimir Bajanov?
Could you show write down Lagrangian for four-dimensional self-dual electrodynamics? I never seen it.
For duality, well, and one example is Born-Eifel.
Sorry?
Here, I mean, okay, there are two differences.
Right.
The models I was talking about, they are non-linearly, the duality that I'm talking about is a non-linear one. So essentially, you can define two things. One is you have a F mu, and then you can obtain a second magnetic field strength by taking the equations of motions. And it turns out that there are models where you have a similar duality between F mu and this G mu that is called normally. So that's the duality I'm talking about. If you're asking whether if I take, for example, Yang-Mills in 4-dimension and I impose the self-duality condition, yeah, of course, the Lagrangian is not easy to define. You need to actually, there are actually approaches that use other type of auxiliary fields. But yeah, that's another problem compared to what I was doing. But it will be actually, I'm actually interested to try to obtain these integrable models starting from there. It's an open problem.
Is it normalizable, TV?
Sorry?
Is it normalizable?
No. Okay. This is okay. So in the case of, first of all, well, one thing that I didn't comment is that all these auxiliary field models, there are few cases that are important ones that are the TTbar ones. And the TTbar, it's not exactly normalizable, but you know that it's quantum well defined. And I mean, the RG flows is still not to know whether it, I mean, it's probably doesn't push you to the UV, to a UV complete model, but it pushes you more to quantum gravity non-local type of models. But somehow it's well defined at the quantum level. And all these other, and the interaction function for in the case of TTbar, it's actually a quite complicated hypergeometric. But we know actually how to construct TTbar by using this, and we expect it to be quantum well defined. So we should be able to study RG flows and etc. in that case. In the generic case, this is all effective field theory. We don't know actually at the quantum level whether this is well defined. Maybe it should be if we try to construct a Smirnov-Zamolodchikov deformation that we know are well defined quantum mechanically because of the work of Smirnov-Zamolodchikov. But in general, yeah, they might be just classical integrable model. They might work as effective field theory in 4-dimension, etc. So it's not clear. But of course, it would be nice to understand it better.
Any further questions? I just had one quick question. You mentioned being classically integrable. What's the meaning of that?
Okay, there are two different notions of classical integrability in the literature. One is just that the lux is flat. So you essentially have flatness of the lux, which is equivalent to the equations of motion of your model. And this holds for this deformation. It's very simple to prove. But then there is a second notion, which is often referred as strong integrability at the classical level, which is not only that the lux is flat, the flatness of the lux is equivalent to the equations of motion of the model, but it's also that you can construct, I mean, by using essentially the monodromal matrix, you can construct the infinite non-local tower of non-local charges, and you need to prove that actually these are in evolution by studying the Poisson structure of these charges. So for the case of the PCM, we have done that, and that is what is normally referred as classical integrability, both weak and strong one. In other models, we haven't done the second step. So we have flatness of the lux for all these models. So we have lux with a spectral parameter, we can prove flatness, but it's very complicated to actually study the Poisson structure of these models. But even, for example, theories like B-Yang-Baxter deformed PCM and etc., or even a semi-symmetric space sigma model, I don't think that the classical strong integrability has even been proved indent deform models for these cases. So this is what we mean in this paper for classical integrability.
Let's thank Gabriele.
Thanks again.
Back